Welcome everyone to the second talk in this year's GHC track. For those who didn't join the previous talk, you can raise questions and have a discussion in the GHC-track-discussion channel on Discord. And after the talk, also have a voice chat in the GHC-voice channel. The second talk today will be given by Divesh Otwani. And with further ado, I'll hand over to you, Divesh.
Thanks. So hi, everyone. My name is Divesh. I'm going to be talking about linear types and linear base. Linear types is a new extension, pretty fresh extension coming to GHC soon. And linear base is an analog of the base package that lets you write practical programs, has all the tools, the fundamental tools you'll need to write like practical programs with this extension of linear types. So let's get right into it. I'm going to be talking, let me describe how I'm going to get into this. I'm going to talk about linear types and linear base through a specific example, and I'm going to motivate this sort of example and this problem right here with this. So the motivation we're going to look at, or the problem we're going to look at, is the situation of wanting to use like fast mutable data with a friendly and pure API. So if you look at, for instance, some of the mutable array APIs that exist right now in Haskell, they have some complexities to them. They have some things that make them not super, like obvious at first glance to use. So, for instance, these sort of type classes for the constructing mutable arrays with a generalization of them with MArray aren't sort of like very, very simple and as pure as simple as pure arrays can be when you first look at them. Like there's a monad around the return value of an array by some index thing, by some element type, and we see some of the similar sort of stuff with mutable data structures for like hash maps that exist within the ST monad. These things aren't as sort of like friendly, but they have their wonderful benefits and all, but like the structure of them sometimes aren't as friendly and as easy to sort of look at as the pure APIs. And one thing I want to say is that there's a super common case of using mutable data structures to improve the performance of your program, but wanting to keep things simple. So this case is when you have like a single-threaded use of some mutable data. So if you have some like state of some data like D1 and you just mutate D1 to some other state, and then you don't use D1 ever again, and then you just keep doing that in like a single-threaded way, then you could actually just use a mutable version of that. And a really practical example of how this improves performance is the change from Idris 1 to Idris 2. So if you've heard, Idris recently, this programming language, Idris, dependently typed programming language written in Haskell, recently went from its first iteration to its second iteration, its second version, and got way faster. And there's a blog post about this that came out like last month. And a key part of why this happened is because something called a global context went from being a pure data structure to a mutable data structure. And here's a little snippet from that blog post. So the global context, underlined in red, is just something that stores all the information that is needed for type checking. And going to the sort of snippet I've put brackets around the bottom, the big difference, the thing that changed was that Idris 2 represented this context as an array with constant time act as an update, and simply had sequential things that sort of updated it, did some other stuff, updated it again, did some other stuff, never using the previous version before the update. And using data structures like this is really common, and in these cases we could actually come up with an API that's a little bit more friendly, mobile, a little bit more comfortable in the eyes, like the pure APIs for arrays and hash maps, instead of APIs that use monads around them and APIs that use the ST monad. So that's basically the motivation, something very friendly and improve speed quite significantly in some cases. So I'm going to talk about this in one of my favorite algorithms of one of my favorite algorithms to work with, and something I really remember well from some of the lectures back in my college. So, and this algorithm is getting a topological sort of a directed acyclic graph. And we'll see that in this case, in this algorithm, you could do this very nicely by sequential sort of updates to linearly threading some data structure, linearly doing updates to it and changes to it. So here is this fun little example of a topological sort. In a topological sort of a directed acyclic graph, what you do is, what a topological sort is you have a directed acyclic graph, like the one depicted on the left. It's an unsorted graph. And a topological sort of this directed acyclic graph is some linear ordering of the vertices, such that if you drew all the arrows from the graph, they would all point forward. And a post order is some linear ordering such that if you drew all the arrows, they would point backward. And so you could find the topological sort or the post order by reversing the other. And so we'll really just find the post order and reverse it. We'll think about reversing it. And a really nice algorithm that I remember very nicely from my school days about doing this is to just keep removing a source and appending it or prepending it to a list. And so this is an example of like linearly threading in a data structure. So we'll take our unsorted graph, our directed acyclic graph, and what we'll do is we'll, in these red numbers, just mark each node by its in degree, by the number of nodes that point to it. And so, for instance, the node 6 has in degree 0, and the node 2 has in degree 2, and the node 0 has in degree 0, and the node 1 has in degree 2. Two things are pointing to it. And we'll call the nodes that have nothing pointing to them, that have in degree 0, sources. And those are the things we'll remove and keep appending or prepending to a list. And so let's start, say, with 0. 0 is in degree 0, and so we'll remove that node, and we'll put that in the beginning of a list. Then we'll look around and see, are there anything, after we do that, we update the in degrees of 1 and 2. And so we could update the in degree of the node 1 to go from 2 to 1, because only one thing's pointing to it now, node 6. And we'll update the in degree of node 2 to be 1, because only one node is pointing to it, node number 1. And then we'll pick another source. We could pick 6. And then so as you see the list on the right, we could pick 6 as the next one and pluck that out, and then update the in degree of the children of 6, 1 and 5. And we could make 1, now if you remove 6 and 0, nothing is pointing to 1. It's a source. And so then you could remove 1. And then, you update the in degrees of the rest. And then if you remove 1, you notice since you've removed 1, 6, 1 and 6, nothing is pointing to 5, node number 5. Its in degree is 0. You can remove 5. And then you could remove 4. And then you could remove 2. And then you could remove 3. And then if you do that, you'll get this topological sort that we see on the right. Okay, so, I added these elements by appending them to this list as we grew. But of course, if you prepended them to a list, if you cons them to a list, you would get the possible post order that I sort of mentioned at the bottom. Now, implementation-wise, if you implemented this algorithm for finding, a topological sort by mutating a hash map that is like an adjacency list, that's a hash map from nodes to children, by successively removing these sources, or even successively changing these in degrees, then you could, that would be a very simple implementation of this, and you could do that with a pure hash map. And that would be, fairly straightforward, easy to read. And so let's look at that, a pure little algorithm for this post order, and then we'll sort of see, like, this is a kind of place where you could improve things a lot by just mutating the structure you're working with, because you're not using the previous version, you're just threading it through. Let's just go through some of the lines. In line 1, nodes will be ints. Line 2, we'll have our graph be a graph of with in degrees, so it's a hash map from nodes to a pair that is the list of children, a list of nodes, and an integer, which is the integree. So for instance, the node 6 will map to the list of nodes 1 and 5 in the image below, and it will have integree 0. So it will map from 6 to the list 1, 5 with the integer 0. Okay, Plug sources is the core part of the algorithm for doing this post order. Plug sources on line 4 takes in a list of sources that exist in the graph so far that are still there, the current list of sources. It takes in a list that is a post order that's in progress of being completed, a post order so far. It takes in an integree graph, and it gives you a post order, a valid post order. And our base case is if we have no sources left to sort of remove or to do anything with. And that's line 5. We have no sources left to remove. We have a post order so far. We have our graph. We just return the post order. In the recursive case, line 6, we have some sources left. We've cons on it, S with some sources. We have a post order so far. We have a DAG. What we do is we look up the children of the source of the first source. And we see if there's no children, right? Doing a lookup of this map, we get a maybe value. We get, and so in this case, nothing in line 7. If there are no children, then, we just have that source that we've removed. We put it in the beginning of our post order. We prepend it, we cons it, and then we recurse. We call pluck sources of the remaining sources with the new post order on the DAG. If there are children, then what we do is we, line 8, we have some children with some integree I, but really, if S is a source, the I should be a 0 in line 8 on that just pattern match. We decrement the kids of all these sources. The decrement all these nodes excess. We decrement all those children. Their integree should go down by 1, and we collect the children that turn into sources after we decrement them. And so decrement kids get sources gives us a pair of the new DAG with the new sources that are generated, a list of nodes, and that's the type that's declared in line 12. It takes a list of nodes that are the children that you want to decrement, takes a graph that you're going to decrement them in, and gives you the new graph, the modified graph, and the list of nodes that have become sources now. And so in line 9, you just take those new sources, we add them to the list of sources so far. Those are a new thing to deal with. We recurse, and we put the source that we just took off now at the beginning of the post order. Very simple algorithm, and this is basically how we could very simply just get the post order. And so for the graph below, you would call this function with pluck sources with the sources right now, which are 6, 0, with an empty list for the post order, and with the graph for the graph depicted below, and you would get out the post order. And this is a very simple, pure algorithm, very easy to cover. Thing is, though, if we have one hash map and we're sort of like doing copies of it in a pure implementation, this isn't as fast as we want it to be. It could be very fast, but it isn't as fast as we could make it. And oftentimes we want something much faster. And the thing is, because this is threaded linearly through, we can keep the hashmap API pure, but make this faster by just mutating it. And so we'll see, like, for the 2 reasons why that we're able to do this with linear types, and how we're able to make this really simple, keep this really simple algorithm, keep some simple code, or rather keep some very clear code that uses a pure API, and have the hash map be mutated. And we'll see these 2 reasons that sort of allow us to do this. Okay, let's get into them. So the first reason is that our single-threaded use allows us to use allows safe mutations. It doesn't allow the mutations to have issues. So let's see what goes wrong when we don't have single-threaded uses, and how single-threaded uses are really just fine. So let's look at an example of a nonlinear use in lines 1 and 2. So this function, nonlinear use, takes in a hash map of integers to integers and gives you a maybe int. And what it does is line 2, it takes the hash map, it calls the function doReads with an insert of the hash map, inserting the key 1 with the value 42, on the left argument, and on the last argument, inserting the same the hash map modified with key 1 with a different value for the different value, 24. And so if this was if insert was implemented by actually mutating this hash map, we might mess things up, and we'll see how. In do reads, line 4, we just take in 2 hash maps and we return maybe int, and all we do is we look up the value for the key 1 in both of them, and we just sum them. That's all we do. Now, if we mutated the hash map in line 2 with the calls to insert, then we would break referential transparency. This same function with the same arguments would have different results. For instance, if we, like call do reads with the copies of the hash map, inserted 142, right, we would have different results than the version now because we're using the same reference. This is a problem, right? And what's happening here is we don't have a single-threaded use. We have 2 references of the same hash map being split apart in line 2. We have hmap being used in 2 places, and that's the problem. Now instead, in lines 10 through 13, we have a example of a function that uses hash maps single-threadedly. So single-threaded hash, it takes in a hash map from ints to bools. It takes in a list of key value pairs and just inserts them all along. And so line 12, very simple. You have no pairs. You just return the hash map. Line 13, you have some pairs. You then recurse by calling single-threaded after you insert the first pair, and then you pass along the rest of the pairs to insert. And in this process, you never use the previous hash map anywhere else. The hash map is just passed along through a successive series of inserts. And if you desugar this for a particular input list of key value pairs, it would just be a combination of inserts on top of nested inside of each other with a hash map all the way inside. And that's basically the idea of a single-threaded use. It just goes through these API functions, comes out of them, and nothing else happens. It doesn't go to two references don't split apart. So when you have this case, basically, if you're never using the other reference and it's never going to go anywhere, why not just mutate it? You could just mutate it and you wouldn't have to make copies, and this would be, in many cases, much faster. Reason 2 of what we're able to do and why we're able to sort of get a nice API with linear types is that this extension, linear types, actually enables us to enforce this single-threaded use. Enables us to statically have a function where we know we're not going to type check the things that we've seen could cause problems. And so I'll introduce a little bit of how linear types does this and what linear types is. So let's look at the first example, limited scope. Limited scope in line 2 takes in the hash map, and it has this hashtag arrow, which is the linear arrow, the only syntactic change that linear types adds, again, the only syntactic change, and returns this wrap type unrestricted for some data type. It's left abstract, contains hash map. And the only point is that that data type somehow will have the hash map inside of it. Thing is, this will not type check. This will not type check. No implementation of this will type check. Why is this the case? Because in line 3, we see the definition of unrestricted, and unrestricted is just the identity data type. It is data unrestricted A, where the constructor just holds the A, and it is not followed by a linear arrow. Now, what this means is for you to write limited scope and put it inside of some contains hash map, and then put that inside unrestricted, GHC will detect that it cannot be sure that you're going to use this hash map only once. There isn't a way; it's not held in a linear way, and as a result, you can't do that. We'll dive into that a little bit more of a concrete example a little bit later. Another pretty much key application of what's happening with linear types is in lines 7 and 8. So this is another sort of big point of what linear types enables. Line 7 is nonlinear split reference. This is something that will not type check, and it takes in a hash map and gives you a bool with a linear consumption, with the linear arrow of the hash map. And its definition is it takes in the hash map and it calls a function do something with h and some insert on the hash map with mapping 1 to 5. This will not type check. Why is this the case? Well, what GHC looks at when it sees this is it sees some function do something, and it needs to know that the linearly bound argument h, that needs to be used in exactly one subterm and used exactly once. So it can't be used in both of the subterms to do something. So you can't split the reference already. That's a problem. And second, even if it was only used in, say, one subterm, but it wasn't used in a way that was linear. If it was an argument to a function that didn't take that argument in a linear way, followed by a linear arrow, then it would still fail. And so in this case, we cannot split this reference where you have do something, take in h, and a different version of h. And so we can't have something break this single-threadedness. That's sort of like the key point there. Now, on the other hand, the function from lines 14 to 17 does type check. And some maps, it takes in this hash map, it does a linear consumption of it, and it takes in a list of keys and things to do on the values if they exist for these keys, functions from maybe bool to maybe bool, and it gives you another hash map. And very simple implementation. If you have no functions, you do nothing, you just return the hash map, and that is a linear use. GHC will look at this and say, yes, it type checks. And line 17, if you have some key and some function to do on it, you can recurse by calling some maps after you call alter, which, in line 19 takes the hash map, takes a function that does this operation on the value if it exists, maybe v to maybe v, and takes in the key, and then it takes in the rest to do. And so, again, the reason why this type checks is because the hmap, GHC looks at it and says, is hmap using exactly one subterm of some maps? Yes, it is. The first subterm is not used in the second. Is it used in a linear way? Is it an argument to a linear function? In some nested, in the nested levels, it needs to be. Yes, it's this first argument to alter, and alter takes in its hash map linearly. And therefore, because alter uses hash map exactly once, and it's an exactly one argument to some maps, and that argument, the first argument, is used exactly once, we can be sure that this implementation uses hmap exactly once. And so that's how we have this wonderful property that single-threaded use is enforced. And because single-threaded use enables us to do this mutation without anything to worry about, we can have this really simple API, or rather we can have this very friendly, pure API and have mutation underneath. And line 22, the conclusion of these two sort of points is that because we aren't able to, if we have a function in line 22 of type hashmap kv, linear consumption to unrestricted some type b, whatever capital B is, we can be sure that this is the entire scope of the hash map. It can't be inside the B because of how unrestricted it is, and that it's single-threaded, it's used in a single-threaded way. And B is some result type. And so we have a way of just completely limiting the scope and making sure it's used in a single-threaded way the whole time. Cool. So what is the result? The cool result of this is that the implementation, the linear implementation of this really cool algorithm of finding the post order is very pure. It's very similar to the one we've seen before. Same sort of setup, pluck sources, line 5. If we have the empty list of sources left, post order, then to use the DAG sequentially, we need to give it as a linear argument to a function. So we use this function lseek, which allows us to discard things which have a consumable instance, lines 21 and 22. lseek takes a consumable A, takes an A, linearly consumes it, takes a B, linearly consumes that and gives you a B. And so lseek will linearly consume the DAG and linearly consume this unrestricted post order. And again, notice in line 4 that if we take in the integer graph and we return something that's wrapped in an unrestricted, the graph can't escape. So we've limited its scope. Line 6, fairly straightforward in the same sort of way. There are some changes that I'll point out along the way. So you have the same beginning, source, you pattern match on the sources, you have a source, you have the post order of the DAG, and then you do a lookup in the DAG of the source, and we have this ampersand with the lambda case, and the ampersand operator is the flip of $sign, so it just takes an argument function. And this is a way of just mocking case statements. Those, since linear Haskell's fairly fresh, it's one of the things we sort of like do to use case statements in a sort of different way. So we pattern match on it. We get out a new type of lookup, which gives us the DAG and an unrestricted wrapping around the maybe value. And so very similar to before, but we have to pass the DAG along in a lookup because we have to consume it. And then we, in a case where we have the first line 7, where we have nothing, we just recurse. We call pluck sources with the S, with the remaining sources, with the first source added to the beginning of the list, const, prepended, and then the DAG. And if you notice, because pluck sources uses the DAG in a linear way, this type checks. Line 8, the same sort of setup. We have some children when we pattern match. Those are wrapped inside of an unrestricted, and as a result of that, what it means to consume a data type linearly after you pattern matched on it is that you just consume only the linear components. Now, unrestricted, as shown in lines 18 and 19, has no linear components. Right? It doesn't have a linear arrow in its constructor or anywhere. And so nothing inside of it needs to be consumed exactly once. It can be consumed however many times it wants. By just pattern matching on it, you've consumed anything of type unrestricted A. It's just consumed by pattern matching on it. And so in line 8, you've consumed the value unrestricted just excess I. And so then you use those however you want, and you use them in a call to a function walk. And walk is the analogy of the thing that decremented the degrees of the children and collected the new sources. Walk takes in line 13, takes in the list of nodes, it takes in the graph, and it linearly consumes that and gives you the new graph with all the in degrees decremented by 1, and an unrestricted list of the newly made sources, the ones that after you decrement them, their in degree is 0. Number of things pointing to them is 0. So you walk on all the children of looking up this one source, and you do a case match on that, and in line 9, you get the new DAG with all the decremented things and the list of new sources, and you just recurse on pluck sources in line 10 with the new sources added to your list of sources, and the source you were looking at prepended to the post order with the new DAG. And it works out again because DAG prime is consumed linearly in pluck sources. And so, we have this linear implementation. We've made a few minor changes, and roughly it looks pure, and it's much more friendly than sometimes you would see with the ST monad or with prim monads and different implementation that use mutable state. And we're able to do this because it's linearly threading this through. And so, walk does some of the similar stuff, and walk actually includes some cool stuff from linear base. So walk, which decrements the degree of these children, the implementation of it is that it calls second on these two arguments. And if you look at line 12, second is something from linear base that just allows you to take a linear consumption function and use it on the second element of a pair that you consume linearly. And this function could mutate whatever it's doing because it's linear. And so we're able to do that. And its first argument is just something that cats maybes over some data structure that could, again, be linear. And this cat maybes, is done over this call to this map accum decrement degree children DAG. And that's breaking that down. That just accumulates this decrement degree function from line 7 that takes in a node, takes in a graph, linearly consumes that, and gives you the new graph and an unrestricted maybe node if that node that you decremented, that you gave as an argument to decrement, is now a source. If now its in degree is 0 after you've decremented it. And mapaccum takes a function like this. It takes a list of nodes to operate on, and it takes the thing it's going to operate on the state, and it does this operation and accumulates the results while threading the the state, the linearly consumed value through. And so with this, with this implementation, you will get, with that sort of map accum deck degree children DAG, you'll have something of type integer graph, comma, unrestricted list of maybe nodes. And so if you just do second to map on the second element of it, and you fmap over the unrestricted cat maybes, you'll get the pair of integer graph with unrestricted list of nodes. And the linear types enable you to do this really nicely. And you see that DAG in this expression is still used in a linear way, right? So DAG is in line 4 in the expression in the second subterm, and it's used exactly once in the second subterm because of the type of map accum. And it all works out from there. And we have some of these like nice little variants that we need from linear base to sort of get this that we can use from linear base to get this sort of working. So summary: linear Haskell plus linear base gives us a pure API for mutable hash maps, and there are two reasons for this. One, single-threaded use of data lets us mutate it in pure-looking APIs, and two, linear types can enforce this single-threaded use. And the result of this, once we have this API, is that the code is pure/friendly and fast. Another thing to note is that basically, we didn't show this, but the allocation function, singleton below, takes in a scope function as its second argument that is a linear consumption of hash map to some unrestricted b and gives you a b. And so, as we discussed, a function of this form, which is the only way to create a hash map, has its limited scope and uses it single-threadedly. And so that's a really cool part about that. Anyway, so thank you for listening. The takeaway of this sort of discussion is that linear types and linear base give us a simple and pure API for fast mutable data, friendly API. And there's a lot more cool stuff in linear base. There's like more mutable data, mutable vectors, mutable arrays, mutable sets. There are two kinds of linear functors. There are tools for interplay between linear and nonlinear code, like unrestricted consumable. And there's tools that replace vectors, but explicitly you control fusion and allocation in them. So, a list that you don't have to worry about when is fusion happening, when is allocation happening. You know exactly when it's happening. And you control that. And resource-safe APIs. APIs like an API for file handles that won't allow you, to read a closed file handle. Anyway, so thank you for listening. And my name is Divesh. That's my email. I'm a software engineer at Tweak. There's also a link for this example that I've presented. Thanks.
Awesome. Thank you, Divesh. That was a great talk. There was a lot of discussion going on in the Discord. Most questions were already answered there, and there's a lot of applause coming, which is great. Maybe it's worth to repeat some of the questions here to also have them on the recording. One, you show a link to the code. Will the slides also be shared?
Yeah, I'd be happy to show the slides. I'm not sure exactly how to do that, but I can coordinate with you.
Okay, awesome. Yeah, we can put a link on the video description and also share it in the channel. There was some discussion about when linearity will be inferred in terms of type inference. Can you maybe say something about that?
That's an ongoing project. Linear types are fairly fresh. So, yeah, that's like a thing that's sort of like happening later. But with some, I found with some like very simple lambda expressions or lambda functions, the inference is fine. But with, like, for instance, polymorphism of linear types, where you have an arrow which could be linear or not linear, and it has multiplicity p. Stuff is quite difficult. Yeah. So, I mean, yeah.
I'm trying to get an overview. There's a lot of stuff that happened. Right. Another question was about what's special about the unrestricted type. And yeah, that was also discussed in the channel. So it's just that it's written in gadded notation with a regular arrow, right?
Yeah.
Awesome. Yeah, I think at this point we can close it here and move the discussion over to the GHC track discussion and also the GHC voice channel. If anyone wants to join in voice chat. Thanks again, Divesh, for the great presentation, and thanks everyone for the great discussion. And enjoy the rest of the rehack. And the next GHC tracks are going to be tomorrow.
Okay. Thank you all.